Hi, welcome to my presentation. I'm Danielle McCool, and I am a PhD student at the University of Utrecht, where I work with sensor data. But specifically, I work with missing sensor data, which is all of the pieces that come between the bits that you actually measure. So my plan today is to take you through the contents of my current project, which is working with mobility data, and we'll try to make sense of all the reasons and possible solutions for the times we don't know people's locations. But first we'll touch on some important bits that are kind of foundational to it, like why is mobility important and what does a travel app do? We study travel behavior because not everybody does the same thing. Although some things are pretty predictable, like if you have a job, you probably go to your work and then you come home from your work to your house. Some things can vary between people, like maybe you only go shopping twice a week, while your neighbor goes 4 or 5 times a week. Maybe you take a car to work, while one of your coworkers takes the train. Knowing how many people commute between cities, or what percentage you're making use of trains, gives transit authorities the information they need to keep things flowing smoothly and predict changes ahead of time. In order to get person-level information on mobility, the gold standard for the last 50 years has been the travel diary. These usually ask people to fill in all trips taken for a single day, along with some associated info. But these travel diaries often led people to estimate fields like time and distance, and filling in fields like mode of transportation and looking up addresses take time from people who aren't really all that invested anyway. So researchers in the field looked to the mobile phone to help reduce some of the tediousness of the task. Mobile phones could get location information from satellites, which could then be used to find addresses, modes of transportation, and routes, the last of which had never been feasible with travel diaries. Let's go back to the route between home and work. Someone's position in space is continuous. So when we travel somewhere, each position we occupy has a set of coordinates that identify it. But when we measure someone's travel behavior, we're limited to a set of discrete points at which we sample the underlying behavior. If the points are close together in time and in distance, then we don't lose much information if we assume the path between them is linear. On the other hand, the further away the points are, the more potential there is for data loss. We call the density of this location information the sparsity. When sparsity is low, our estimations are likely to be good. But if our sparsity is high, we may underestimate distance traveled if we fill in the gaps linearly. So all location data we collect is sparse to different degrees. The Tabby app asks for someone's location once per second when moving and once per 3 minutes while still. This would be a pretty low level of sparsity if the data collected matched up with the rates. But the reality of data collection is that it always provides you something unexpected. There are a number of factors that influence our ability to capture someone's location. Let's start with some related to someone's locational circumstance. Remember that it's not the phone itself telling you its location, but an interaction between the navigational satellites and the device. If the signals can't get passed between them, we can't get a location. This happens in tunnels and with underpasses, but the signal can also be blocked by buildings, both the one you're in and any potential buildings that are tall enough to block overhead line of sight. That's an urban canyon. Sometimes the data aren't collected for reasons related to the device. Maybe the battery runs out. Although in practice we found that rarely to be the case. This shows the average battery life for the users of our app. And as you see, although it does decrease over time, it rarely makes it all the way down to 0. Often the device itself just kills the app, and you're left waiting for the user to manually open the app again before you start receiving location updates. And sometimes the device's operating system will enter doze mode, or hibernation, and restrict communication with the navigation satellites. Lastly, there's always the chance that the user turns off the phone, closes the app, or turns off GPS ability. Some users install the app and never enable location permissions. In those cases, we have a location sparsity of 1. Whether the sparsity impacts our estimate of distance or not is largely a factor of whether the person was engaging in travel behavior at the time. Think about a person at home whose phone is receiving the same coordinates every 3 minutes. No movement means the continuous location isn't changing, meaning our discrete sampling of it is doing a perfectly fine job. Now let's pretend that the respondent is still at home. Only now they turn off their phone for a few hours. When they turn it back on, it's still at the same location, just like in the other situation. Since they didn't actually go anywhere, there's no underestimation if we ignore the missing time and just go ahead and calculate our statistics anyway. Metrics like distance traveled and number of trips will still be accurate. Only the problem is that on the researcher's side, we don't actually know what happened in the interim. All we see is the increase in sparsity and associated potential for biased estimates. But first, let's take a moment to look at how the sparsity plays out in the data that we collected from our respondents in the app. So, Q can be calculated across different resolutions, over trajectories, days, or observation periods, if you want to characterize the differing patterns of missingness. Because we expect movement behavior to differ over the days of the week in accordance with work-related travel, it's useful to look at sparsity over the days of the week. We can also look at sparsity over time, since we had many participants who participated for not only the full week but also much longer. There's evidence of a change in Q with respect to time in the study. Later days of participation are correlated with increased sparsity. The intuitive interpretation is that as people fall out of the study, they spend less and less time in the app. Someone's last day will almost never have a high sparsity because they'll end their participation somewhere in the middle of it. But there's another alternative explanation that may give us some more insight. Devices that send less data may ultimately have longer survival curves, maybe because people find it less intrusive, but possibly because iOS devices lend themselves toward allowing apps to run in the background without killing them, with a trade-off of unreliable processing times. Which we can see if we look at the difference here between Android and iOS. We can look at how many days elapse between the first and the last timestamp someone records, based on their OS, in order to see if that's a sensible idea. And we do see a small difference. On average, iOS users make it 4 days longer than Android users. Both operating systems have restrictions that limit processing power during nighttime hours, but the actual effect on mean sparsity is relatively small. Here you see a differential pattern of the actual location data and the amount that was sent over the days of week and time of day. If we know that sparsity is more or less the same during the evenings, even though the number of locations we're receiving differs, that allows us to feel more comfortable using sparsity as a metric for determining whether or not location data are missing. In order to start to understand these issues, we designed a simulation study on the basis of just the full data from our respondents with very low sparsity. Using this, we could simulate missingness under different conditions and see what happened if we then estimated our aggregate measures as normal. First, we took out the location data at random in 5-minute intervals to recreate various levels of sparsity. In this condition, we found that increasing sparsity led to an underestimation of distance traveled, but the relationship wasn't linear. In fact, mild to moderate sparsity didn't decrease distance estimation much, which makes sense. This is like cutting off corners when points are further away. You still get some distance, just not all. Next, we varied the time period in which the data would be missing. Missingness at night or during the workday could be caused by hibernation of the phone or turning it off for bedtime, both of which would imply that the device wasn't currently in motion. Preliminary analyses are not yet available, but seem to confirm our suspicions. Increased missingness in the evening has very little impact on estimation of distance. Finally, we can start to imagine what we might be able to do with the big gaps in people's data. Obviously, if we miss a week for someone, or even a day, the most obvious way to handle that is just by imputing the aggregate measures for that time period. But suppose someone misses a gap of a number of hours. It should be possible to impute some characteristics about that time period. If we find people that are similar to the respondent with the missing data, and we can match other characteristics of the missingness itself, like the length, or the time of day, or even the place where it started, then we can do a better job of improving our estimates. In the best case scenario, we might even find that we have sufficient evidence in someone's routine behaviors to allow for one day to completely predict the next. This is such an example from my own data, in which I made the same trips to the same places repeatedly. If the locations match up closely, a person's own data could ultimately predict their missing travel behavior quite well. Well, looks like we've got a little time left, so I'll go ahead and jump into something I've kind of glossed over until now. So, okay, think back to one of those routes with the points. Doesn't really matter which, so let's just choose this one. Let's zoom in on one part of it. This was my route, so here's me, then, actually, walking along one part of it. As I walk, I'm generating coordinates of the rate of 1 per second. So let's plot my actual trajectory with time along the x-axis and longitude along the y-axis. You'd expect a nice line because I'm only walking east and west, and I'm walking at a regular interval. But it turns out the reality is actually quite different due to the measurement error from the whole GPS chain of events. It's messy and unpredictable. This comes from a few different reasons, which I don't need to touch on now, but here's a real-life example of what the data look like when there are multipath errors. This person wasn't moving in the first 3/4 of this video, but the data make them look very mobile. Let's say we want to know how far someone has traveled on a given day. If we were to add up all the distances between all these points, we'd be off, maybe in this case by an order of magnitude. So instead we've got to be clever. Here's the algorithm we use. It draws lines fit between segment endpoints. Endpoints are progressively selected at the points that have the largest deviation from the line until it reaches a stopping point where all the points are fit within the tolerance that you set. But what should the tolerance be, you ask? Great question. Well, we didn't know either, so we did a simulation study. Here's the distribution of all the distances in our complete data. And here's how that distribution changes if you apply segmentation at error levels of increments of 10 meters. At 10 meters, that means we keep making new segments until all points are within 10 meters of the segment. At 200, we stop when it's at 200 meters. Notably, this stops making much difference when it's around 60. The more segments you create, the closer you get to giving each 2 points their own segment, which would correspond with an error condition of 0 meters. Here's a different route, with a comparison of the naive distance up there in the left-hand corner versus the distance after segmentation. Note how the biggest difference comes during the stationary periods. The algorithm actually does a pretty good job of removing noise in these sort of situations. So, in short, one of the really important parts of migrating to using this type of data for mobility research is that we come up with some sort of way to intelligently handle this missing data. Because even in the best of circumstances, we're almost certain to have some missing data. And that missing data is likely to be related to the travel behavior itself, so it's not ignorable. We know segmentation isn't appropriate when we start filling in these long gaps where we're not sure what's happened between. But there are long gaps where we're relatively sure of what happened between, and in those times segmentation is appropriate. When it's not appropriate, we have to be clever about the missing data one step up. We can't impute somebody's route unless, of course, we can be pretty certain that they're taking the same route that they took yesterday or the day before. And so we have to impute at an aggregate level so that we have the characteristics themselves instead. I welcome any questions and comments you guys have, and if you are interested in knowing more, I can send you some papers that I've written so far. But thank you for coming to my presentation, and I'll see you in the chat room.